Hey there, we're about to do Google Code Jam round 2. Starting in 1 second. Okay, let's go. Alright, 4 problems. So today the top 1000 advanced to round 3, like it says here. Hopefully we can load the problems. Oh, you got one of them. And just swapping any two. Then the minimum of arrangement. Is that 4? Is it 2? Okay, yeah. Oh, so large ranges are cheaper. So 6 is like, is 6 log n? Oh, we can do swaps. One of 100. That's one. It's not too bad. That's the third problem. Retiling. What is it? Okay, but you can just do the whole thing, get the minimum, and then swap it to the beginning. No, that should be totally fine. Testing tool. Okay, cool. Great, let's go. Have this. So I guess technically this is that. Okay, so let me see. Okay, so basically, yeah, we're just gonna Did anyone get this yet? Oh, nice. All right, hurry up a little bit. So basically, we're gonna query I through n. I'm gonna do the swap, and then we're gonna say done. All right, let's run this code. Give it a try. Yeah, I don't use test case. So I was saying 4. Let's do solid 4. And then, I guess I'll say 1, 2, 4. Say 2. Okay, cool. I think that's good. Oh, right. Local. So a where test number is ignored. S21. I'm not allowed to. Why does that have to be? Okay. S52 1. Why is that happening? Oh, it should be I minimum. That is. What is happening? S2 1. I don't understand. What is M return? What the heck? How did I get? How did this? Am I? What is happening? Where's? Did it not print? D. Wait, how do you transition? D and then D returns 1. Whose idea was that? Okay, great. Alright, gonna move on. Some people have already done this one as well. Okay. Okay, so they have to be divisors. Great. So we finished A, we can move on from that. How big is it? 10 to the 6th. Okay, so 10 to the 6th, which means a rough idea of what we want to do here. And we're just gonna oh, how did that happen? This is too slow. Okay, so no, it's not. It's not too slow. Okay, we submitted. Are they all visible verdicts? Hidden verdict here. Hidden verdict, okay. 46. Wait, is that a penalty? That is a penalty. Come on. Sample failed TLE. What? 20 seconds here. 40 seconds here. Did I use more than 20 seconds? What is the point of this? Okay, so okay, and then now we're gonna do some optimization stuff. Best current. Let's if current that made it slow. Oh, that's very frustrating. What am I supposed to do with this? Why is this TLE? This ran fine. What is happening? I could just call recurse 1 0 But you can't have 2, so no. This is not correct. Yeah, that's not correct. I mean, it definitely runs under 40 seconds. Well, what is the problem here? Maybe it runs more than 20 seconds? That's so dumb. If this works, that was just really dumb. All right, let's keep going. Oh, they're all different. Okay, so 1, 2, 2. Okay, so I just scan over n, and it's, I see. Why? Oh, you get the V's. That was super dumb that I had to do that. I didn't change anything from the algorithm. I just had to make it. Okay. Anyway, we're gonna move on. this. Okay, let's basically this up. Yeah. Maybe I should. So it's the longest increasing sequence from the top down. Not the longest increasing, just the greedy. Just the prefix maxes. Wait, so if the number goes up, you know this number is less than the number next to it. The count goes up. It's greater than this. You should have a bunch of inequality chains, right? Oh, that's not a chain. Oh. what the max value is. Oh, I got +0 because I got the. That wasn't a penalty. I see. Figure out which value is the max value. Yeah, and then you can divide them up however you want. Okay, so ah, don't have it. Resolution. Use persistent array and then I would be good at this. Do I just switch into this one? Sigma end. Let's do this. What am I doing wrong? I need to put a type. That's fine. Okay, I guess we're child changing from oh, right, 0 was 10. Okay, so the easy version, we can just use many flips as we need. So we should just do swaps. We should only do swaps greedily when we get two for ones. And then it's, I guess it's a max matching problem. Do they all just solve the small? It's possible. It's just a max match. Smurf flips we need minus the max match. Cost I need with. If S is at least 2F, then we should never do a swap. So swap with minus 1. Just 2 flips. What if F is much bigger than X? We can do the whole thing with swaps sometimes. What if F is bigger than X? Let me just minimum swaps. So then, is this still a flow problem? Might still be a flow problem. I mean, I could already solve the small for this, but do I want to do that? I think so. Oh, is that so? You do flow on how many? That might be what it is. Okay, I think I have the idea. So you have 1 and a cost. No, I'll just do this. I don't think it's necessary, but there's no reason not to. Right, and then backwards. Where did this? The cost times swap plus flips is twice the flow. Okay, what happened here? I guess I just do this. Oh wait, what? Oh no, forgot to flip these. Okay, now we actually have paths in the flow. Okay, this one is a little tricky. I'm going to it also might be too slow. Oh. I need to test this, so let me see. Okay, so how do we do this? I guess I just make it be big. So it's 2 A's. One, 10, 10. This is the right format, right? Yep. Okay, so and then we just replace A with G, B, F. Okay, it seems very fast. Because it's fine. Shorty jar for C. least one, so it gets to about long. Okay, that's pretty fast. I'm not going to have to worry about it. Do both pretty fast. These are not hidden perks. Okay, yeah, I expect my rank to improve over time because people will resubmit these two. Alright. Oops, let's do that. Alright. Okay. So here we go. I think yeah. Alright, I think it feels pretty good where I'm at right now, so I can explain my solutions to each of these problems. So here, problem A, we have minimum sort. So in this problem, we need to sort a list of 100 integers in increasing order. What we can do is we can swap any two positions, and the other thing we can do is query the minimum of a range, where we give it a range and it tells us the position of the minimum. And then it has this weird thing where a larger range is cheaper to query than a smaller range. And we need to do this with a certain number of coins based on this formula. It turns out all we have to do, it's really simple. So first we just query the entire range 1 through n. We find the minimum and then we just swap it with 1, right? So now the smallest value is first. And then we just repeat that with 2 through n. So 2 through n, we find the minimum and then swap that with 2. Then 3 through n, we find the minimum, swap with 3, and so on. And you can just show that with this formula, you know, basically you're getting 1 over n plus 1 over n minus 1 plus 1 over all the way to 1 over 2. And for n equals 100, that is definitely less than 6. So this is code. So code is pretty simple. Just made a query function, made a swap function, and then a done function. And yeah, you just find the minimum from I through n, swap the minimum with I, and then after all of that, you're done. So yeah, this was the first problem. Definitely the simplest one. All right, here we go. Second problem, Matrygons. So basically the idea is we have a regular polygon with like it's more like a bunch of layers of regular polygons. And for each consecutive pair in the layer, it's like contained in the next polygon. And in particular, the vertices have to match the vertices of the next polygon. So this triangle has 3 vertices, which are 3 of the 6 vertices of this hexagon. This hexagon's 6 vertices are 6 out of 24 vertices of this icosahedron. I've never heard of that. And the point is 24 plus 6 plus 3 adds up to 33. So we've stacked like a layer of, or we've stacked 3 layers of polygons with 33 sides. Another way you can do 33 is to do 22 and then 11, which is 2 layers. So we're given n, which in our case was 33. We want to know the largest number of polygons we can stack together to get a total number of sides of n. And n is going to be up to 10 to the 6th in the worst case for test set 2. So the key observation here is that in order to do this type of stacking, where the vertices coincide, the smaller polygon, the number of sides has to be divisor of the bigger polygon's number of sides. So 3 is a divisor of 6, 6 is a divisor of 24, that's how it works. And here 11 is divisor of 22. Yeah, so basically the idea is when you have 11 and 22, well 22 divided by 11 is 2, so we're just going to use every second vertex. And for example, 24 divided by 6 is 4, so we're going to use every fourth vertex, right? And that's the idea there. So yeah, for this problem, I didn't do anything too smart. I just have a recursive function that starts with the smallest polygon and then just decides what the next polygon is and just decides what the next one is after that. And it does a recursive generation process. And because the numbers grow pretty big pretty quickly, you can't do too many different versions of this recursion. So yeah, this is my code. It's actually really simple. The one thing that turned out to be really dumb in my case that I had to handle was the time limit here is 20 seconds, whereas the time limit here is 40 seconds. And locally, my locally my code runs in about 11 seconds, but apparently on the CodeJam server it runs in more than 20 seconds, although less than 40 seconds. So I just had to, here it's 12 seconds. I just had to add some code where it only computes up to 10 to the 6th if it has to. If it doesn't have to, it only computes up to 1005 because of this. So that was kind of silly, but that was enough to get it through. Yeah, I got TLE on the sample. Yeah, it's kind of silly, but anyway, that's what we did. Okay, hidden pancakes. So for this problem, basically we're making stacks of pancakes and we're trying to talk about how many pancakes we can see from the top. And you can only see a pancake from the top if it is bigger than every pancake above it. So for example, here we can always see the top pancake. This pancake we cannot see because it's smaller than the one above it. And then this one we can see because it's bigger than everything above it, right? And then once we add this one biggest pancake on top, we can't see anything below. So we're given these numbers for the first pancake, for the first 2 pancakes, first 3 and first 4, and so on. How many pancakes are visible? We want to know how many ways we can arrange our n pancakes that ends up with this sequence. So I didn't have maybe the best solution for this problem, but the main observation I made was that we know what the at any given point we should know which positions are the kind of the visible pancakes at that point. Because, for example, v1 is 1, so this 1 is the visible pancake. v2 is 2, that means they're both visible. v3 is also 2. What that means is the new pancake, the top pancake is always visible. So basically, because we lost one visible pancake, it had to be this one. And in general, for example, if you know which positions are the, let's say v equals 5 visible pancakes right now, and then the next v equals, let's say 3. So maybe to make this more concrete, the example I made was like this, where these would be the visible pancakes at this point. So, okay, so I guess v equals 4 here, and now we're going to add a 7 to the end. Well, what happens here? The 7 covers up the 2 and the 5, but it doesn't cover up the 8 or the 9. So this is v equals 4, and this is v equals 3. So basically, when we go from v equals 4 to v equals 3, we know that we're going to get this one. So we know that we have to lose the last two visible pancakes. So we still know that here the visible pancakes are in this position, and this position. Basically, if we follow the v array, we can figure out for every prefix of the v's, or every prefix of the pancakes, what are the visible positions. And then the key insight that I had was, at the end, the earliest visible pancake at the end, that has to be the biggest pancake, because the visible pancakes at the end are just the suffix maxes, and the like very the very last suffix max, or in this case the earliest one, is going to be the max of the whole thing. And when we have the max of the whole thing, we can just choose to distribute. We know we put the max number there. We can just choose to distribute the remaining numbers either to the left side or the right side. It doesn't matter. So that's a choose function right there. And then we can recurse on the two sides. So that's the main idea. Unfortunately for my solution, I ended up having to use a persistent array to get this to work, because I need to access the visible locations from the different prefixes. But the main idea is, yeah, to simulate the process with the persistent array and then just do the recursion that I mentioned. So we find the max, and then we recurse on the left and right. And the choose functions, it turns out they simplify into just a factorial and then some divisions. So that was the main idea there. Yeah, so this was, I'm sure there's something better that doesn't require this persistent array, but this was how I ended up doing it. Okay, and last we have problem D. So for this problem, we've got an R by C grid, and each tile has, in the grid, has a color of either magenta or green. There's two operations we can do. We can either flip a tile, changing the color from magenta to green, or vice versa, or we can swap two adjacent tiles without flipping either. And we want to, we're starting from some arrangement, for example this, and we want to end up with some target arrangement, for example this. And we know that a flip costs F, and an S costs, sorry, and a swap costs S. And we want to do the minimum cost to get the goal, right? And so R and C are both up to 10. In the first test set, F and S are both 1. In the second test set, they're up to 10 to the 6th. So the way I thought about it was, let's think about doing the, we can always change the order of the operation. So let's just think about doing the swaps first and then doing the flips after. So we do some set of swaps, and then afterward we just flip the positions that are not the right color. So we need to do one flip per wrong color. So in terms of the swaps, if F and S are both 1, the only swap that makes sense is a swap that fixes two values at once. The reason for that is because any other swap that doesn't fix two values at once, you're better off just doing flips, right? Because if the swap fixes two values at once, that costs 1, whereas two flips would cost 2. But if you're fixing anything less than two values, then you could just replace what you're doing with flips. So we're kind of just starting with the assumption that we're going to do flips for everything, and then you can actually solve it as a max matching problem, as a bipartite matching problem, where basically you can match two things if their swap would fix both of them. And yeah, so we can just run max matching, and that will tell us, essentially tell us how many flips we can save with the swaps, and that'll be the solution for the test set 1. For test set 2, things are more complicated. Basically, the main idea I had was we can think about, again, kind of like matching up these swaps and then finishing things off with flips. But now the it's not necessarily true that you would only do adjacent things. You might do things that are pretty far away, especially if flips are a lot more expensive than swaps. So we basically end up making a graph where I connect on one half I have the G's that want to be M's, on the other half I have the M's that want to be G's. And essentially I try to connect these. The cost is the amount of steps it takes to move in between. And I can compute this way the min cost to reduce the number of flips we need by a certain amount. That's the main goal here. And so then for each of the possible flow values, which reduces the number of flips, we're going to figure out the min cost to get that, in terms of swaps, to get that number of flips. And then we're going to consider that as a potential best option. So basically taking that number of swaps times S plus the reduced number of flips times F. Yeah, so a little bit hard to explain, but this is kind of the main idea. It's still the same idea of let's do the swaps first, and then let's see how many flips we can avoid that way. And based on that, we're going to figure out the right trade-off of swaps and flips. Okay, so that's the idea here. And that's it for this contest. Let's see, what place I'm in. I guess I'm in 53rd right now. We'll see how that ends up. Hopefully everything that I submitted works out. So anyway, that's it for me for this video. Yeah, feel free to subscribe to the channel if you're interested in seeing more videos, and I'll see you in the next one.